All right, so I wanted to make some code here for a beta product that I want to force people to update the firmware on. And so what I've done is I've just created this proof of concept code right now. And what this does is it determines whether the firmware was uploaded since the last reset. So has the customer installed new firmware? And then we store our device's runtime, probably in hours since EEPROM is write limited. On the Mega series, it's 100,000 writes per byte. And then we need to prevent code execution if the firmware hasn't been updated recently enough. So the use case here is 40 days. So basically, if the customer hasn't updated the firmware in 40 days, then the code won't run. And then, of course, once the customer does upload new firmware, we need to make sure that the code execution is allowed to resume. So again, the whole point of this code is to make it to where if the customer doesn't update the firmware on their device, it gets bricked basically after 40 days, and then it's recoverable. So if they just load new firmware, this will go away during the final production, as I've stated already, and yeah, so. This is just because I don't want old code out there. So basically, we have to read all of this data from EEPROM. And basically, when you read in EEPROM from an 8-bit MCU, you read it 8 bits, 1 byte at a time. So most of this is basically, we have a function here to determine if the firmware was just updated. And the way that we do that is we look at the build date. So build date is a built-in function. It's required by the C standard. And it's a 12-byte function, or it returns 12 bytes, which is in the format of month, day, year. And this is, for 2 examples, January 23rd, 2022, or March 5th, 2022. We don't actually care what the days are. All we need to do is see whether or not they've changed. If the user installs the firmware on January 23rd, and then they don't install it again until February 5th, that's fine. We'll reset to 0 there. This is not an exact science. It's not 40 days from the exact moment you installed the firmware. It's just 40 days since the last time the firmware was installed. So we basically store that here as a constant. So every time you compile the code, which is clicking this button here, that's going to update this. So if the date has changed, you will get a new value stored in there. So we also have this EEPROM address map where we basically are telling it where to look for the data here. So the Arduino, every time you power it down, all the RAM gets wiped, and so the only place we can store is in the EEPROM, and the Mega has 4 whole K of EEPROM memory. We're only using, I think, 14 bytes of it, so it doesn't matter. We're not even, we're using 0%. So we need to see the compile date, which I just described, and then we also need to store the hours since the last update, so that after you hit 40 times 24, so 40 days, in hours, we can brick the device basically. So these are the addresses where we can find these data in EEPROM, and then here is where we're going to store them in RAM, so when the device is on. And so the first thing we do here in our setup, and again, this is just a proof of concept, I'm going to roll it into the main code tomorrow. We're starting our test, and then we're going to basically read the compile date from EEPROM into RAM, and we have to do this 1 byte at a time. So Arduino does have an EEPROM.get and put library that can do data types for you automatically, but it is not well written, so I just kind of wrote my own. I'm only doing fixed width reads here, so this is pretty simple. We're just reading each byte into RAM. So we have this character array where we're going to read the date. Again, I don't really care what the date is. I just want to know if it's changed or not. And once we've done that, now we have our date in memory. We're going to look at the, let's see. Oh, next we're going to read the hours since the last firmware update. Again, this is a 16-bit unsigned integer, and you can only store 8 bits in an EEPROM address. So we're just reading these uint16 here. It takes 2 calls there. And now we have all of the data we need in memory. We've read everything from EEPROM. So now we're going to just say, hey, look, here's the hours since the last update. And then we're going to just output this uint16, which we just read from EEPROM. That's what we're doing here. And now we're going to, I don't know why we're saying EEPROM read there. that's an old thing. It doesn't need to be there, so I'll just delete it. Again, this is a proof of concept. So now what we're going to do is we're going to say if the firmware was just updated, then we know that the customer just loaded new firmware. Well, how do we know if the firmware was updated? The dates are different. So that's this function up here. Let's see, was the firmware just updated? So what this does is we start and we just say, hey, let's just assume that the dates are identical. This is the date from the compiler, which is stored in program memory, and then it's the date from EEPROM, which the program can store, which we'll get to in a minute, but it only stores it if the dates have actually changed, because that means we've uploaded new firmware. We'll look at that in a second. So anyway, at the beginning here, we assume that the dates are identical, and we're going to compare the dates 1 byte at a time. We're going to look at the EEPROM date, and then we're going to look at the program date. And so we're going to just go through the bytes and date. It's 12 bytes. And that is, again, a function of the C standard requires you to have the 12 bytes of January 23rd, 22, whatever. So that will always return that way. Okay, so now we're going to go through and we're going to just compare it. And if at any point the dates are different, so if it's January 24th versus January 23rd, then if at any point any of those is different, then we're going to say the dates are not identical. And, so that's that. And then we're just printing out the characters just because it's a test program. We'll get rid of that eventually. And then at the very end, if the dates are in fact identical because all the characters were the same, then the firmware was not updated. And so we're going to return a false here. So was the firmware updated? It was not. And otherwise, then we're going to say the firmware was updated. So back down here in our setup file, okay, so if the firmware was just updated, then the customer just put new firmware on. So we need to reset that counter to 0. So this counter here is when we break the device. So this is, what is it? Yeah, EEPROM address hours since update. And again, this is a 16-bit unsigned integer, and we're writing into an 8-bit memory space. So we need to write it 2 calls at a time. And then we're going to store the new compile time too. So because the compile times are different, that means that the firmware was just uploaded. Well, now we need to store the program date in EEPROM so that when we boot again, the values are now the same. And that would mean the customer has not updated the firmware. So after we do that, we just continue to main. And then, so the other case, the firmware was not just updated. So now you've reset the device again. You haven't uploaded firmware. So the firmware did not change since last power up. And we have just a define here. We're going to say hours and 40 days. And of course, there's more than 30 hours and 40 days. This is just for test purposes here. And I'm not even using hours. This will be the final code here. So if hours since last firmware update is greater than the hours in 40 days, which again is 40 times 24, but right now we have it set to 300, then we're going to eventually, the LCD screen is going to say, hey, update the firmware. For now, we're just printing it out, debug, we're just updating the firmware, and then we just enter this while loop forever and it never returns. If you did want to get rid of this feature, you could just delete this line of code, but I don't recommend doing that. There's a really valid point on why I'm doing this. This firmware is in a very beta state, and as it changes, it will get better, hopefully. And if you disable this and allow the firmware to just stay out there forever, that could cause problems in the long run. So I just fixed a huge bug today that was fun. So that's what the point of this is I want this code to not last more than a month because we're in an open beta. So, and then once this is the verification check here, and then this would just be the normal LiBCM code running, the normal end use code running, and all we're doing now is we have a for loop here it's going to print it out. I'm going to show you this actually working here in a second, by the way. So we're going to just print the hour count. And then we're going to delay for 200 milliseconds. So obviously an hour is more than 200 milliseconds, but for this test code, we don't want to wait, 300 hours or really whatever that is, hours, 9,600 hours or whatever. We don't want to wait either of those. So, and then of course, every hour we are going to update the number of hours in EEPROM. Now again, because the EEPROM space, right, is write limited to 100,000 writes, we won't actually write every hour. We'll write at every key off event probably. If you turn the key off 100,000 times, you're only driving like a mile every time you drive a car. And again, this will go away eventually. So long term, I'm not too worried about it. But this will be replaced. And then, of course, again, because it's a 16-bit number of hours that we're having to write, we're having to do this over 2 calls. And then we just have a while hang here just so that we don't write the EEPROM in our testing here. So we'll go ahead and run this now. This is our serial monitor, and I have the Arduino here. I'm going to basically be resetting it a whole bunch. So I'm going to clear our output, which is already clear. I'm going to reset the device. And the test has started. So the customer has not updated in 40 days, and here's what we're doing. So we started the test at the top where we said test started, and then we read back the EEPROM for the date code, and then we're going to compare it here. So we're comparing the EEPROM byte to the program byte. So that's the EEPROM byte, program byte. You can see in this case they are identical, which means the customer has not updated the firmware, and the time period has elapsed. Hours since last update was 305. So we need to update the firmware. So I have changed the date on my computer, so I'm going to update new firmware, and while it's doing that, I'm going to clear the output. And so we've now just put new firmware on here, and we're going to say, hey, look, in this case, the firmware was updated. I don't know why it says not updated. I think, oh, there was a second reset there. Arduino resets it while it's running, so don't worry about that. That's just an Arduino issue there. So anyway, you can see that this test is running. In this case, you can see that the dates were different, presumably. Now again, the Arduino reset too quickly, but you can see we are running. So I'm going to push the reset button now, and you can see that I'm holding it down, so the code is not able to run at all. And you can see we're at 152 is our value. I believe it's only going to be 151 that we restart at. And when you see, we can see that the hours since last update was 151, and you can see that we've started now 151, 152. And we're going to just keep doing that, 156. And right now the limit is 300 hours. So when we hit 300, the device will continue to run while you're driving. And then the next time you turn the key on, the IMA system won't work. And that means you need to update the firmware, obviously. And I'll probably put something on the screen to where you can see how many hours you have left, just so you're not suddenly whatever. But again, the guidance is that you just do it every month. Hopefully you're updating even more than that. So I'm kind of pushing the key down, 238, 239, 240, blah, blah, blah. So we'll let it go ahead and get up to 300 here, which is going to happen in a sec. I'm kind of watching these numbers here. And at this point, we've hit 300. Again, LiBCM is going to keep working as long as the key remains on. And then the next time you turn the key off and then turn back on, now the device has bricked itself again. So that's all this code does. You know, the complexity of it is just that we're having to read and write from EEPROM. Again, Arduino does have a built-in handler for this, but it's very bad. I have a handler I use in some other projects, but it was kind of a jumbo jet. We didn't really need it for this, so I've kind of just written this one from scratch. So anyway, that is how this feature will work. Again, I'm not trying to hide it in any way. I'm just trying to force people to use it. So yeah, that's how this works.